Hello, do you hear me, Chandan?
Yeah, can you hear
Okay.
me?
Yes, you can start.
Okay.
We're on time. Go ahead.
Okay. Um, Hello, everyone. My name is Chandan Bose. I'm an assistant professor of aerospace engineering in the University of Birmingham. And today, this training is on the dynamic meshing strategies in OpenFOAM. And this training has been prepared by me and Joel in collaboration. And in this particular presentation, I will mostly use the materials that are available in the tutorial wiki of OpenFOAM and the tutorials online available by the Wolf Dynamics website. So you can easily download those materials for free and try it out and follow this presentation. So let me first introduce ourselves. Who are we? I am Chandan, as I said already, and my research interests broadly lie in the areas of unsteady aerodynamics, nonlinear dynamics, and fluid state interaction. And Joel is already very well known in the community. I will let Joel introduce himself.
Keep going. Go ahead.
Okay, so uh, yes, so let's go ahead in the presentation. So as I told that these two are very important references for this training session. One is the OpenFOAM wiki tutorials, which has many other tutorials along with all the test cases available for the dynamic mesh motion. And the other reference is, which is very helpful in this regard, is the tutorial section of the Wolf Dynamics website. So the agenda of today's presentation is basically giving you an overview of dynamic mesh capabilities of OpenFOAM. And the disclaimer is that this presentation or the training session is targeted towards the beginners of OpenFOAM to intermediate users. So I will not have time within this 1 hour to show you very advanced example, but I will try to summarize all the different capabilities that OpenFOAM has so that you can go in deeper and try to find out what type of dynamic mesh motion can probably be the best suited for your application of research or industry application. All right. So the few examples that are very well known in the OpenFOAM capability is the mesh morphing, overset meshes, moving meshes, sliding meshes, and adaptive mesh refinement. Now, within the time frame of today's training session, I will mostly discuss the mesh morphing and the overset meshes, and I will just touch upon the other three capabilities very briefly. So as I told that it is a beginner level introductory training session, and the tutorial cases that I will be showing are tested for the ESI OpenCFD versions, OpenFOAM version 2106, 2112, and also the higher versions it works. And it is also expected to run with the .org fork of OpenFOAM with slight change of keywords. And this is very important. I apologize that I am not being able to present it in person so that we can try it hands-on. So I will try to present it like a seminar, but any question or query regarding the presentation and the test cases that I'm showing can be directed towards me through email, and I will personally answer all of them, or to Joel, who is an expert of the field, obviously. And feel free to post your queries in the question and answer forum. So let's begin here by giving you a fundamental basic of what we mean by dynamic meshes. So the dynamic meshes is the capability by which we allow the mesh motion. Okay. And why do we need mesh motion in our simulation is just to accommodate the moving bodies or deformation of the meshes. All right. And what does it mean in terms of the governing equation? It means that if we are solving the main primary governing equation according to the Eulerian Lagrangian arbitrary of Lagrangian Eulerian framework, then we have to accommodate a grid velocity or the mesh velocity in the convective term of the governing equation. Here, phi is a very general state variable which can be different things. And now this mesh motion can be achieved through different ways. One is morphing, which basically is the diffusion or smoothing of the maze or deformation of the maze, or it can also be achieved by adding or removing new cells. It can be achieved by sliding some region of the maze. It can be also achieved by some overlaid disconnected component meshes, which is under the category of overset meshes, which we'll discuss in a while. And the bottom line of this discussion should be that these dynamic mesh motion strategies, they are not particular to any physical model. So the different category of the mesh motion strategy that I will be presenting here should work for any physical model or any solver that you use for your problem using OpenFOAM. Now, you have to keep in mind that all the different applications or the tutorials that are available in OpenFOAM that has not adopted to mesh motion, that can be because the problem does not require the mesh to be moved or deformed, but it does not necessarily mean that the dynamic meshing strategy cannot be adopted for that solver. Now, why do we need dynamic meshes? As we started the discussion, now what is the physics point of view? The physics that we want to capture in our simulations may require the body motion that can be prescribed, or that can be due to the multi-physics. For example, fluid structure interaction, where your body can move due to the effect of the flow, or it can undergo a flow-induced vibration. And this kind of vibration can be rigid body motion, where the body is not deformed, but body undergoes motion in different degrees of freedom along the 6 directions in the 3 dimension, or it can also be deformed due to the effect of the flow in the fully coupled fluid structure interaction problems. And also, we might also need to refine or unrefine our meshes based on the different scalars that we want to track through our simulations. So in all these cases, we need dynamic meshes. So for example, the 3 different examples here I'm showing, the first one in the left shows the mesh example of mesh morphing, which I will discuss in detail in a while, where you can see that a cylinder is undergoing a prescribed oscillation in the cross flow direction. And you can clearly see how much deformation the connected mesh elements are undergoing through the morphing of the mesh. The second one shows you the flow field of a flapping airfoil. And there you see that the mesh component has 2 parts. One component associated around the airfoil rotates. However, the elements of those mesh does not get deformed, and the outside component of the mesh remains as a straighter. And this can be achieved through an arbitrary meshing interface. And the third example in the right-hand side, you can see is called adaptive mesh refinement, or AMR, where actually we refine or unrefine the mesh by tracking a physical variable. In this case, as you see that a droplet is rising to the interface level. So we track the alpha water, which is the ratio of the volume of the air and water. And based on that, we refine or unrefine our mesh. Now, the other very distinct category is the overset mesh, where, as I said, we have multiple disconnected mesh elements one over the other, whereas the bottom mesh element components will be the Eulerian meshes, which will not move, but it will be overlaid with a overset region, which will move disconnectedly, as we can see in the right hand part of the mesh motion, where we actually see an airfoil undergoing a flapping motion in an overset manner. However, we can visually compare these 3 different mesh motion for the same example. So the objective of showing this is to give you a physical perspective of how in 3 different approach we can achieve the same physical problem, or we can simulate the same physics. All right. And the example here is the flapping airfoil, as you can all understand. Now, this overset capability has been now available in this OpenCFD version, and there are plenty of tutorial on that, but I will go into the basic in a while. So coming to the very first level of application, that how do we implement this dynamic mesh motion strategy? As we all know that if we are beginner, we know that at least in our session case, we have three different folders: zero, constant, and system. And within the constant folder, I will have a dynamic mesh dictionary within which I have to mention what type of dynamic meshing strategy I want to use. And the first step of it would be to assign a motion type. Okay, I'm coming in detail what do we mean by the motion type, but you have to keep in mind that this motion type has to be assigned to a patch or a cell region, or it can be applied to the whole domain depending on what type of dynamic meshing strategy that we are going to use. And particularly for the adaptive mesh refinement, as I've already mentioned, we have to define a scalar field which will be used as the refinement criterion. All right. And the last that the boundary condition of the has to have the boundary condition of either calculated or moving wall velocity. Now, if we want to look at the OpenFOAM installation directory and first have a perception that what are the different type of dynamic meshing libraries that are there they are already developed within these OpenFOAM libraries, then we have to go to solvers and we can very easily grab this dynamic fvmesh.h, and we will get a list of whatever libraries uses this dynamic mesh motion strategy within the source code directory. All right. So if you are with a terminal installed with OpenFOAM, you can easily go and grab this, and you can see depending on the different version, there will be more and more different libraries that has been added to accommodate the dynamic mesh motion solvers. Now, this is something I want to start with before I go into categorically in each of these different dynamic mesh motion strategies. That what these motion solvers that I mentioned already, that mention motion type to a patch or a cell region or the full volume, right? What are those motion solvers? And particularly if we want to incorporate the fluid structure interaction and the two-way coupled motion of the mesh, then the very well-known library, which is 6 degree of freedom rigid body motion library, and where they are located. If you are starting with OpenFOAM, so you might be quite confused. So where do we find these motion solvers? So that's why, keeping that in mind, that is for beginner level, I just want to quickly show you. Can you see my terminal?
All right, what was the question?
Can everybody see my terminal?
Yes, yes.
Yeah. So here, as you see that I am using the OpenFOAM version 2112, and once I go to the source code directory, I see that there are different folders, but particularly if you see the dynamic mesh folder, and if I go to that folder and I see what are the contents of it, we here see again another folder called motion solver. All right. So if we go to that folder and see, we will see there are different motion solver, which I'm going to now show you. So, and most commonly used are the displacement based motion solver and velocity based motion solver. And if you go again further into a source code directory, you will get that there are these libraries: rigid body 6 degree of freedom rigid body motion solvers and the 6 degree of freedom rigid body state solvers. All right. So this is just to show you the location of these files. And then going back to our discussion, that is the place where we find these motion solvers and the 6 degree of freedom rigid body motion solver libraries. Now, again, the last thing I have to do before discussing particular things is to tell you why do we need to really take care for the particular numerics or numerical scheme for the dynamic meshes application. Because we need to adjust the solver settings according to what type of intricacy in the physical problem that we want to go into. All right. Because dynamic meshes have more stringent stability and accuracy requirements than static meshes. And during simulations with moving bodies, the boundaries mesh domain will experience strong instantaneous acceleration, large displacement or deformation, and fluctuations in linear and angular velocities. And specifically for arbitrary mesh refinement simulation, since we refine or unrefine the mesh, the CFL or the Courant number criteria will change from one refinement level to another. And it's extremely important to control this CFL number and be sure that it remains constant within the limits of stability. Otherwise, our solution will diverge. And it is also recommended to monitor the mesh quality when dealing with the morphing meshes, particularly if we want to remesh it for some specific problem, such as we want to simulate a falling body case with 6 degrees of freedom, which does not have any constraints. So in that case, if we want to use mesh morphing, we really need to remesh the problem again and again manually. And for that, we have to monitor the mesh quality as we go along the deformation of the mesh. So due to these reasons, we have to really keep in mind that we need to tweak the solver settings properly based on what type of dynamic meshing strategy that we want to use. All right. And it's intrinsically unsteady, so there is no question about it. And also, they are computationally very much expensive. All right. So the first category that we want to discuss in detail is the mesh morphing. And it's also known as mesh diffusion and mesh smoothing technique. And this motion, as I already mentioned, that it can be predefined functions for giving you prescribed motion of the body. It can be rigid body motion, or you can also incorporate any complex kinematics of the body. Let's say you don't know the nature of the kinematics and the kinematics is obtained from an experiment. We can incorporate any such arbitrary motion of the body through an input table, okay, which contains the body's linear displacement and angular displacement as a function of time. All right. Now, this I have already mentioned that for particularly morphing meshes, we have to very much careful about the corresponding CFL number, and the time step must be chosen in such a way that it allows for a smooth mesh motion diffusion in the domain. Otherwise, the solution will diverge. Okay. And we have to monitor the mesh quality, as I mentioned previously. Now, let us see into these two categories. One is the prescribed motion of the body using the predefined function, which is already defined in the OpenFOAM directory, such as very canonical periodic sinusoidal or cosinusoidal motions like a sin omega t or a cos omega t. We can directly apply the predefined function. All right. And we have to mention it clearly within the dynamic mesh dict file. And what are the components of this kind of motion that we need to define? The first thing is we have to define the mesh motion library. And the mesh motion library in this particular case is seen to be dynamic motion solver FB mesh. And when you grab that dynamic mesh keyword, you get many such mesh motion libraries which are available within OpenFOAM, and you have to use one of them. And within that, we have the motion library file, that is the lib.so file, which is here libfvmotionsolver.so. And then we have to mention the motion solver, the directory that I showed you. Now, these motion solvers can be of different types, and which I showed you now is the mainly two type is the displacement based motion solver and the velocity based motion solver. Now, then we have to actually mention what type of method we want to use for implementing this motion solver. In this case, you can see that is a Laplacian diffusion based method. So next we have to give the displacement Laplacian coefficient, which is a function of diffusivity, all right? And what type of Laplacian diffusion method you want to use, and I will show you what are the different types available. In this case, we use the mesh diffusion method of inverse distance, and then we have to mention either the patch or the cell region or the volume of cells that we want to move. And in the left hand side, in this case, you can see that the example of the moving cylinder case, I have defined the boundary of the cylinder as a patch and named it as cylinder, which is my moving boundary. All right. Now, you might wonder what are the other different types of solver and diffusivity method and prescribed motions are available. So these are the list of it, and you can get it easily from the source code of the OpenFOAM by grabbing the keywords. So it can be displacement based or velocity based, Laplacian motion, particularly it can be based on SVR stress method, it can be multi-solid body motion solver, etc. And equally, the diffusivity method can be chosen as inverse distance, inverse volume, inverse phase distance, inverse point distance, and so on. And it can be also motion directional. So I will try to pick some of the examples which fits to these different methods and try to compare them for your sake of completion, but you can always go back to the tutorials and change this type of solvers, diffusivity methods, and so on, and play around with it. And the different prescribed motion that we have based on angular oscillating displacement, which means whether your body is pitching or it is moving angularly in an angular motion with a prescribed angular velocity, or its motion is just translational. In that case, you can use the oscillating displacement or oscillating velocity. And there is an advanced version of time varying mapped fixed value, where actually you can hard code a function of movement that you want the body to exhibit. All right. And here is an important comment, which is move dynamic mesh, no function object, which means that it will not run your solver, but you can use this move dynamic mesh comment to see how your mesh is exhibiting the dynamic mesh motion strategy. All right. So let's look into the one of the prescribed motion, which is predefined motion, is oscillating displacement. And as I said, it is oscillating means it is a periodic canonical sinusoidal motion with a prescribed amplitude and prescribed omega, which is its velocity in radian per second. And those are the input values. And sorry, omega is basically the frequency here. And then the value is uniform, which is a dummy value for ParaView to understand this. And here the important thing is the built-in motion function is oscillating displacement. You can change it to any of these function, which is oscillating velocity, or if it is a rotational motion, angular oscillating displacement or angular oscillating velocity. Now, here you have to, as I already mentioned, the moving patch cylinder. So we have to remind to change the boundary condition of the moving patch to moving wall velocity. All right. Now, the last thing that we need to incorporate to run this moving body simulation is that we need to solve the new fields, cell displacement and diffusivity for incorporating this mesh motion and morphing. For that, in the FV solution file, we need to add a new linear solver for the field cell displacement. And also in the dictionary of FV schemes, we have to actually add the discretization scheme relating to the diffusion method, which is Laplacian as a function of the diffusivity and the cell displacement. All right. And you can use the default discretization methods such as Gauss linear limited 1.0, and there are different order of accuracy of these methods, and you can try playing around to match any reference results. Now, in this case, which I forgot to mention, that in the 0 folder, you have this point displacement file where you have to define this motion details, and if it is the velocity based motion, you will have a point motion U file. So these two files will be different whether you are using a displacement based motion or a velocity based motion. Now, here are some visualizations. So you can see that till now, the case that I was explaining to you can be visualized with this exaggerated zoomed in view, so that you can understand how the maze is moving. And if we go to the second category, where we do not have any particular canonical motion that we know of, but we need to incorporate some arbitrary motion, let's say, that we observe in the experiment, but we do not understand what is the functional form of it. In that case, we can actually use a very handy function which is called tabulated 6 degree of freedom motion, which is nothing but it is like a tabular file in the .dat format, which has to be included in the constant folder. Okay, and the syntax is something like that the library is solid body motion displacement, and the function is tabulated 6 degree of freedom motion. And in this case, the first column is the time, and the second column is the translational motions, and the third column is the rotational motion. So in this file, as you can understand, that I have first a y directional motion, then I have a x directional, and then so on. You can understand. So let us visualize what does it lead to. So in this case, we see that first it goes up, then it goes right and comes back and does whatever I have mentioned in that tabular value. Now it can also include the rotational motions also. So let's imagine instead of a cylinder, I have a rectangular plate, so which I can move linearly with an angular fashion and with any random arbitrary motion that I can generate through my expected or I have a tabular time instances of that motion. Even I do not want to generate, I got that from experiment and I want to simulate that, I can just input it as a tabular value. However, we can also use this time varying mapped fixed value capability to also hard code the functional value of this arbitrary displacement. So so the next thing is, how does these diffusivity models, how does the diffusivity functions, different functions actually affect the maze quality? Now here I show you two example of two comparisons. One is with the inverse distance method, and the other one is the exponential point with the coefficient 0.6 exponent inverse distance method. And as you can see that, sorry, I think it's exponential, yeah. So as you can see that in the second case, the quality of the maze is worse, but it is subjected to the problem that you want to solve. So you have to choose these different diffusivity models based on the physics that you want to capture, and you have to try and see what type of diffusivity model works better for the particular application that you want to simulate. All right. Now we can also simulate multiple oscillating cylinders. Okay, and that can be prescribed too. And for that, the library is the same, dynamic motion solver FBMS. However, the motion solver is also the same. The changes comes from the diffusivity, where I have to mention actually the two patches that I want to move. In this case, it is I have two cylinders which I name is cylinder 1 and cylinder 2, and if you apply the same displacement Laplacian and inverse distance diffusivity method, you can actually simulate the motion of two bodies. So here I also list the other methods that you can possibly use. One is inverse volume, quadratic, exponential, uniform, directional, and so on. And also, as I mentioned earlier, it can be displacement Laplacian motion solver or the velocity Laplacian motion solver. All right. So all these, I need to again and again mention this, all these example problems are very systematically provided in the tutorial of the Wolf Dynamics website. So you can download each of these cases and play around with it so that you can understand how these different motion solver as well as different diffusivity models affect the mesh motion. All right. So here, two cylinder cases, as I have already shown you in the previous slide, has been given the oscillating displacement motion and with a particular amplitude and omega value. And you can see in the first, in the commented portion, you can see the above one is +4 and the below one is -4. And the second case is in the horizontal translational amplitude 200. Now, if we can observe these two cases, we see that two bodies, two cylinders are going up and down for the first setting, and for the second setting, it actually, the first cylinder goes up and down and the second cylinder goes sidewise. Now, there are severe limitations of multi-body simulations using the mesh morphing, because when these two bodies or multiple bodies, they undergo huge deformation, the mesh quality degrades considerably. So the non-orthogonality or the skewness parameters of the mesh, when they go beyond the threshold value, the solver actually fails and the solution diverges. So in that case, the alternative is to use the multiple disconnected mesh components, which falls under the category of overset method, which I will show you in a while. So you have to keep in mind that mesh morphing is quite limited in my experience for simulating multiple body motions. So here is another example, but everything same using mesh morphing. I use the displacement Laplacian, and for the diffusivity, I use the quadratic inverse point distance. And I have two airfoil in this instead of two cylinders, and you can see that within the limit of the parameter space, particularly for the low amplitude motion, we can still use mesh morphing and can generate the flow patterns behind these tandem bodies. And you can have a visualization in the right hand side how the mesh would morph with this motion. All right, so we can use it, but the bottom line is that we have to know the limit of the parameter space that we want to simulate. And in terms of accuracy, mesh morphing has higher level of accuracy compared to other methods, because here we are actually deforming and morphing the whole mesh. If we are within the limit of the mesh quality measures, such as non-orthogonality and skewness, there is no interpolation involved. So of course, the errors related to the interpolation are not there. So it, in my experience, gives a better accuracy for capturing the appropriate physics. All right. Now, the second category of the problem, if the motion is not prescribed, but due to it's induced due to some other agent, such as, let's say, flow. If the motion is governed by the fluid and undergoes a coupled fluid structure interaction, so how do we simulate it? Of course, so that capability also is available within OpenFOAM. And in that case, we have to use the rigid body mesh motion solver or rigid body motion solver, which has the lib rigid body mesh motion.so lib file. And in this case, because this is a two-way coupled phenomena, we, along with the flow solver, we need also a structural solver which solves the governing equation of the structure. And in this case, because it is a rigid body motion, it doesn't deform, but it moves along multiple degrees of freedom. We need a solver which can solve the oscillator equation, all right, which is nothing but mx double dot plus cx dot plus kx equal to forcing. And OpenFOAM has multiple such solvers, and here I show you two examples. One is symplectic, another is Numark, which actually takes into account the numerical integration of Numark beta method. And each of these different numerical integration techniques has their own parameter value, such as Numark has the two parameters, which is beta and gamma. So not only the prescribed motion, but also the flow induced motions can be simulated using mesh morphing. However, here the dynamic mesh will have other details such as the constraints, the restraints, the mass, the inertia, stiffness, which are required to calculate the structural displacement. All right. And the forcing comes from the fluid forcing, either aerodynamic or hydrodynamic forces. All right. So at this point, Joel, do you see any questions in the chat box? Because I can't see anything.
Excuse me? Can you hear me?
Yeah. Do you see any questions in the chat box?
Let me see. No.
Okay. So I think we are good to go ahead as we don't have much time left. So the second category of the method that we want to explain or show you is the overset method. And as I have already mentioned, that overset meshes are the approach in which we have multiple component meshes which are disconnected to each other, and some of them are Eulerian and some of them are overset, which moves overlaid on another. And using this overset mesh, actually we can carry out simulations involving complex motions such as 6 degree of freedom and FSI. And in this case, none of these component meshes deform or morph. So we can actually incorporate any degree of displacement that we want to, which will not lead to the divergence of the solver. However, we have to keep in mind when we use this overset method, we have the inherent interpolation involved, which incurs some of the numerical errors that we have to be well aware of. All right. And so overset mesh consists of multiple component meshes, and the connectivity between the connected mesh and the background mesh are obtained through proper interpolation in the overlapping areas, which are termed as the overset patches, which we will see in a while. And these overset patches can actually theoretically intersect each other, and even then the solution doesn't diverge. That's one of the most advantageous feature of these overset meshes. And as I said, that overset meshes can add numerical diffusion to the solution, and the interpolation is non-conservative, which costs the loss of accuracy in the solutions. And in the overset meshes, the cell size close to the overset patches should be similar to minimize the interpolation errors that comes from the experience, and the coarser mesh determines the error level. So at the connecting patches, if the cell sizes between the different connected component meshes are far apart, there are considerable interpolation errors which can lead to erroneous simulation results. Now, before we can actually perform the overset mesh simulations, we have to do some sort of pre-processing. The step one would be to generate and merge the component meshes. And here one thing has to be noted, that all these different component meshes has their own case files involving their own zero, constant, and system folders. And once the meshing is done separately for these component meshes, they have to be merged together for running the final case. And so after merging these component meshes, we have to define the overset patches. So that's very important. And we have to also assign the zone IDs which actually determines the grid priorities. All right. So here you can see that in this schematic, we have three level of disconnected mesh connected through overset patches, which is shown in the white dot lines. And the colors denote that there are three different grid priorities starting from 0 to the background mesh, then 1 which is used is as a refinement zone, and 2 to the overset region. All right, and which actually tells the solver to compute its stencils and assign the cell type, and then to understand where the interpolation has to be done. Okay, and as you can see that within that orange overset regions, we have a region where there is no overset cells, but we can see the background refinement region, and that region is called hole. So basically in the compute stencil, we have actually three different type of cells which can be determined by the cell type. One is the hole, second is the interpolated cells, which where the interpolation happens, and the other is the calculated cells where we solve the Navier-Stokes equation. And now within the interpolated cells, we can classify it to be two different types. One is acceptor, which receives information from the other cells during the interpolation, and others are donors, which actually send information while interpolating. Now, the most important part is the numerics, which are considered in this overset mesh motion strategy. So as you are already now known to the fact that we have different level of interpolation involved, we need some interpolation method, and which we define in the FV scheme directory. So it can be normally the three different type of interpolation schemes are available in OpenFOAM. One is cell volume weight, which is first order accurate. It's fast, but it has problem with hole detection. The second one is inverse distance. It's second order accurate, it's bounded, but it's computationally very expensive. And the third one is least square, which is second order accurate. It might become unbounded depending on other type of tolerances that we use during the simulations. It's computationally expensive, but its accuracy level is comparatively higher. Now, if we want to get more information about what type of interpolation is happening and what are their details, we can actually switch on this debug switch in the control dictionary, which is very handy in my experience. We can say overset 1, and then in the log file, we get the details of these interpolation methods. So here are the same two problems that I have already demonstrated using the mesh morphing example. One is prescribed motion flapping airfoil. Another one is the 6 degree of freedom fluid induced motion of the cylinder. And you can see that the beauty of overset meshes is that the different mesh components, we can actually prepare them in any third-party softwares or in any way we prefer to make it, and then we can just merge them all together. So the first example of flapping airfoil actually shows you that both the mesh regions are unstructured meshes prepared in Fluent, and then we just import it into the OpenFOAM using Fluent Mesh to Foam and then merge them together. Whereas the second example shows you the structured meshes prepared using the block mesh utility. So that is the another advantage, that if we need to accommodate a very complex geometry, we can actually only mesh the overset region around that complex geometry with a lot of accuracy, but the background Eulerian meshes can be just rectangular structured meshes created using block mesh utility, which actually saves a lot of time while preparing the meshes. And also it is helpful to maintain the mesh quality. So I just want to show you another very interesting capability incorporated recently in 2106 version, which is called driven linear motion, which actually saves a lot of computational time while we need actually a large background mesh for a problem. Let's say in this example that I saw, it's a pendulum, it's a simulation of a pendulum motion, or it's a projectile motion, sorry. So the second example that I actually wanted to explain to you can be done using a pendulum motion also. So in this case, or in a more practical approach, more closer to my research problem, if I want to actually simulate a freely falling body when subjected to gust, it can actually go anywhere. So to capture the motion for a long time, we need a very, very big domain with a very big background mesh. However, if we want to maintain the same level of refinement along the whole domain, it becomes unfeasible to simulate. So in that case, we can use the driven linear motion capability to stick a refinement region with the center of mass of the body that you want to track, and it follows the translational motion along the body, and this can be achieved using the solid body motion solver, and the solid body motion function is driven linear motion. So I found it very useful for very specific problems, which can also be useful to you too. All right. So now with that, that is the limited information that I can give within the time frame. And I move now on to the three other types of dynamic mesh motion that we can do. One is the moving meshes, where actually we move the whole volume of the mesh without any deformation. And what type of problem that we can simulate? We can actually simulate problems like sloshing, where we actually do not need to deform the mesh, but we need to move the whole domain. That can be also prescribed, as well as fluid structure interaction induced motion. And for that, our motion solver is solid body, and the solid body motion function is multi-motion, and where we can incorporate oscillation as well as rotation with prescribed amplitude, omega, and axis of rotation. All right. And then what are the other type of solid body motion functions available? It can be axis rotation motion, linear motion, multi-motion, oscillating linear and oscillating rotating motion. SDA is the shift dynamics motion, which can give you a 6 degree of freedom approach. Then again, we have a separate 6 degree of freedom motion and solid body motion function. And this is the example of the sloshing that I wanted to show you, where for this kind of physics, we need to move the whole domain, and this kind of approach can be very useful in that sense. And the fourth kind of dynamic mesh motion is the arbitrary mesh interface method, where it actually involves different sliding meshes. And the example that I previously shown you using this is the flapping airfoil motion, where we have a separate rotating part and the outside stator part. And within the rotating part, it undergoes a sliding motion at the interface of both these mesh components and achieves the motion of the body. All right. And the solution is interpolated back and forth between topologically separated these two regions in this case, which one is rotor, another is stator. And this interface is actually called the arbitrary mesh interface, where the interpolation is done. All right. And to reduce the interpolation errors at the AMI patches, the meshes should be similar in both the master and the slave patches, which we call the rotor and the stator patches in other ways. Okay. And one most important point, that what is the limitation of this method? The method, in order to use this method, we need an axial symmetry for both of these component meshes. And this is the example that I was talking of, that I have two different mesh region. One is actually rotating, which gives me a lot of advantage in terms of saving the computational resources, because I do not need to rotate the whole region, and also we can incorporate multiple bodies detached with each other, which does not give the problem that we face for the mesh morphing region. But of course, it comes at the cost of interpolation errors, and the motion can be described as the AMI, cyclic AMI type of motion, and where we have to actually mention the neighbor patches, which is very important. So each of these rotor AMI and the stator AMI cases, I have to mention what
excuse me, Chandan, you have 10 minutes.
Sure, I'm almost done. So we have neighbor patches of stator AMI and the neighbor patch of rotor AMI for each other. All right. And these are the settings that you can dig in deep while applying this method. So I'm almost on the last point, so that we can at least have 5 minutes of discussion, and Joel is there with you to answer if you have any queries. And so basically the last part is the adaptive mesh refinement, and I will just touch upon it. And as I have told that in this type of dynamic mesh motion, what we do, we actually set a scalar field based on which we introduce the refinement or unrefinement in the mesh. All right. So in the settings, we use the dynamic refine FB mesh and dynamic FB mesh, and the dynamic refine FB mesh coefficient has different settings. Those are very important to achieve appropriate mesh refinement. One is the refinement level, how often we want to refine or unrefine, like per time step, per iteration, and so on. And then what is the scalar field? Here in this case, let's say temperature T, which is the quantity of the interest. And then we have two levels between which we try to refine the meshes. And we have a maximum number of cell cutoff limit, where if we go further beyond that, we stop the refinement, or we keep on doing the refining and unrefining cases. All right. So OpenFOAM has multiple tutorials related to it. So the basic tutorial of this dam break tutorial with an obstacle I have taken here, where you can see that we have the same dynamic refine FB mesh, and the conditions are, we have used a default 1 level of refinement interval, and the field here is the alpha dot water, which is again the volume ratio of the air and water, and we have two levels, lower and upper limit of 0.001 and 0.999, between which it does this refinement. And we have other nitty-gritty of the details which are not very important, but the most important is the maximum cell count. If you really want to limit a threshold to the refinement and unrefinement level, you can use the maximum cell limit also. And this is also another important development that I want to show you, that somebody can come up with the question that is the scalar field the limiting one, or we can do it also on the runtime basis. And so in this community development, the link is here in the gradient AMR. You can see that it's an example. I just want to show to you so that you can go back and check it. Is that we can calculate the velocity gradient also on the runtime with the slight modification of the code, and then track that as the tracking criteria for doing the refinement or unrefinement. All right, so this is a very interesting option, which gives you the outlook to the fact that it cannot be, it is not only to be explicitly mentioned scalar variable, but it can also implicitly be calculated during your solution, and also in turn can be tracked for doing the refinement and unrefinement. So with that, I actually close this tutorial, or in turn I should say this is a presentation. It's not a hands-on tutorial because I'm doing it virtually. But as I said again, we have 5 minutes for your queries and doubts, which I cannot maybe do it very robustly, but Joel is there who can answer to you. And all these tutorial cases are available online in the community. So I have not used any private tutorials, but still, if you have any query or if you need the case files from me, you can shoot me an email and I can personally answer to you. Thank you for listening. Thank you, Joel.
Okay, thank you very much, Chandan. I just need to add something to what he showed, that all this stuff needs to be updated. I already have it. I will see it when I release, but in OpenFOAM 11, everything changed as you are used to, that they changed something this time for the better, but many things changed, and also the overset, there are some modifications. So many things don't apply. Pretty much I would say everything don't apply anymore, but all the improvements are for the better. So hopefully by the end of the year, I think I would release everything updated. So are there any questions on the floor? One question is regarding the AMI interface. So the slide, for example, for sliding mesh that we classically use for rotating machineries. Do you have any special recipes or advices in the way you decompose the in processors? I mean, do we need to keep the both AMR, the slave and the master, onto the same processor or not, in order not to lose too much performance?
Yeah, I think in my limited experience, I have also faced problem when I have tried to decompose the domain, separating these two different parts. But actually, I think it's better to try to keep it within the same processor, but I do not have a clear answer to it because I have not really investigated this problem. Maybe Joel, do you have any better experience with it? Hello. Can you hear me? Hello.
There was someone there. Yes, go on.
Sorry, I couldn't listen to anything actually. So
no worries. I just have a question on the overset mesh interpolation schemes.
right.
If you go to them, it said that the inverse distance and the least squares were second order. Now I've been using overset mostly in foam extend, and when I use the inverse distance scheme, I only get first order convergence. So if I'm using a second order interpolation scheme, should I get second order convergence from the solver?
I see. Okay, so in my experience, actually, I have got second order convergence, but I think Joel is a better person to answer to that because he has used a lot of overset method. I actually don't know your answer.
Let me address. No matter you read, even in commercial software, these are non-conservative first order. That doesn't exist at all. So if you read somewhere, they are not setting interface. Are there any more questions in the floor? Okay, there is a question in the Q&A. Can you read it? And then maybe you can address that one.
The last one, I'm starting from the last one. Can we apply AMI to two rotors rotating against each other? So in this case, I think there should not be any problem because the stator part is disconnected. I mean, there is interpolation, but there is no mesh deformation in between. So I think if you have sufficient distance and the AMI patches are quite distinct, there should not be any problem in applying rotation to different orientation of the rotation, if I understand the question correctly.
Okay, so I think we're in time. So for everybody, please send the questions to the Q&A in Huba. For Nicolas, also send your question to Huba, and then we will try to answer that. So with that, yes, thank you very much, and thanks again, Chandan.
Thank you everyone, and feel free to email me if you have any specific questions.
Okay, so with this, we're ready, we're done. So